You'll notice in your book that one of the moments of inertia they give you is for a thin rod that's rotating about its center of mass. So if it's spinning in this direction, okay? And so we say that the length of the rod is L, okay? And it tells you that the moment of inertia is equal to the mass of the rod divided by 12 times the length of the rod squared. Okay. Now, what happens instead if we decide that we want it to rotate about one of its ends? So we notice this is going to change the moment of inertia because now we're rotating around a different point. And first, let's think about why. So here, so we have a point on this side that's, that's some distance, and then there's a point on the other side that's the same distance away. The furthest point from the axis of rotation is here, which is a distance, this distance is r equals L over 2. And then the same thing on this side. But now, if we're looking at them rotating around the end, we have some points that are much further away. We have some points that are distance L from the axis of rotation, which is further than L over 2. And so we would expect, since the moment of inertia, right, our formula for the moment of inertia is the mass times the distance from that point to the axis of rotation squared. This is squared, so this is saying the further away we go, that's actually having a bigger impact than just changing its mass. So changing this point that we're rotating around has a large effect on what the moment of inertia is. So, so we want to find a way that we can move this axis around. And so the way to do that is with something called the parallel axis theorem. So you could go and you could evaluate, the integrals for all these objects, but sometimes it can be very difficult if you're not evaluating the moment of inertia about its center of mass. So what the parallel axis theorem is, it says let's take the moment of inertia for some place that we know. So, so for example, we know the moment of inertia about its center of mass. And then we say the new moment of inertia is the moment of inertia about its center of mass plus the mass of the object times h squared, where h is this distance. It's the distance that we've moved the axis. So this only works if the axes of rotation are parallel, right? So we see that both of these are just, it's a rotation about the y-axis. And so these axes are parallel, so we can just shift it over using this formula. So in this case for the rod, then we see that this is m over 12 L squared plus m. In this case, h is L over 2 squared. So this is ml squared, 1/12 plus 1/4. So if we get a common denominator, then we have 1 plus 3 is 4 over 12, which is 1/3. So we see that the moment of inertia is m over 3 L squared. And so indeed, this is a much bigger moment of inertia than what we had when we were going about the center. And so this is going to be useful because sometimes on the exam I may give you an object and ask you to calculate its moment of inertia, and it might not be one that's given to you on the exam. It may be something like this rod, where you have to be able to shift, you have to use the parallel axis theorem to shift and find what the new moment of inertia is. So we notice something very important here. It's that the orientation of an object makes a great difference in what its moment of inertia is. That's not true for mass, right? It doesn't matter, how you're holding an object. If you're, if I have, something like a textbook, right? And if I have it upright, it has the exact same mass as it does if, if I turn it on its side like this, or, if I open it. these are all the same. But that's not true for the moment of inertia. Each one of these would have a different moment of inertia. And even in the same orientation, if originally I'm going about this axis, and then I start spinning around this axis, right? These are going to have very different moments of inertia. So make sure you work these problems, and probably even, I think your book also doesn't cover the parallel axis theorem. So make sure you work some Halliday-Resnick-Walker problems that involve this, because you'll definitely be seeing this type of thing on your exams.